Hello friends, so today we are going to continue with, you can say, electrostatics, and today we are going to solve 3 questions, okay. And all these 3 questions are from electrostatics. One second. So the first question, it states that a thin rod of 10 centimeter carries a total charge of 24 ESU, that is 8 into 10 to the minus 9 coulomb, uniformly distributed along its length. Find the strength of the electric field at each of the 2 points A and B located as shown in the figure. So we are given 2 points A and B, and these 2 points, one is on the axial line, okay, that is a B, and point A is along its axis. And for that we have, let us draw this figure, and okay, let me modify here only. So let us call this one end as x is equal to 0, and let us assume that L is the total length of the rod. Then the other end will be called as x is equal to L. Okay. And so we are given, total charge is given to us, that is our Q is 8 into 10 to the minus 9 coulomb, and length is given to us, that is our 10 centimeter, or we can say that will be equal to 0.1 meters, and this charge is uniformly distributed along entire length. Therefore we can find out the uniform charge, linear charge density. You can say linear charge density, which is our lambda, and lambda will be equal to Q upon capital L, and this Q upon capital L, this will be coming equal to at 8 into 10 to the minus 6 coulombs per meter. One second. So this will be our 10 to the power 8. And now we can use the basic formula for our electric field, and that we are going to write that, let us consider a, okay, let me, so this is our x equal to 0 and x is equal to L, and then we are having, this is point A, and this point A is, let us put at a distance D. So this will be at x is equal to minus of D, and from the other end this total distance will be equal to D plus L. And on this rod, let us consider a small element, and this small element is of length dx having a charge of our dq, and it is at a distance of x from the origin, that is x is equal to 0. Therefore, we can write that electric field at A we can write the general formula, and the general formula is our dE is equal to, this will be k, and we have this as our dq upon r square, and here r is nothing but equal to d. And we can also write that our small charge dq will be equal to the linear charge density multiplied by the length of this element. And so we can write that our dE electric field for point A will be equal to our k dq is our lambda time x, dx in this case, and r will be equal to our d plus l. Sorry, r will be equal to d plus x and whole square because of this small element. And so the total electric field at point A, because of this entire rod, we can integrate it from 0 to L, and we get this as our, this as the integration of this, and so we substitute it, we get this as E of A. This will be our k lambda integration 0 to L, and this will be our dx, and we get this as our d plus x whole square. Now we can just evaluate our integral, and it will be coming as our k lambda, and this will be minus 1 upon x plus d, and the limits are from 0 to L. Therefore, we get that electric field at point A will be equal to k lambda, and this comes as 1 upon d minus 1 upon L plus d. And we can further solve it. We can have k lambda, we can take this LCM, this will become as t L plus d, and this will become as L plus d minus d, and here d and d cancels out. Therefore, we get that electric field at point A will be equal to k lambda L upon d and L plus d, and all the values are known to us. We simply substitute the values, and k is our 9 into 10 to the power 9, lambda is our 8 into 10 to the power minus 8, and length is our 0.1, yeah, 0.1 meter, and divided by, we have our d is the distance, that will be equal to our 0.03 multiplied by 0.13. So its solution will be given that our electric field at A will be equal to 1.84 to 10 to the power minus 2. This will be our value of electric field at point A. Now we come to electric field at point B. field at point B. Field at our point B, and our point B is somewhere here, and this is our x equal to 0, and this is our x equal to L. And let us assume this is our y, and y is our 5 centimeter, or we can say 0.05 meters. So B lies at the perpendicular bisector. So you can say point B lies at perpendicular bisector, and for this let us change the coordinate. We take this as 0, 0, so it will be minus L by 2 comma 0, and the right side will be plus L by 2 comma 0. So perpendicular bisector, and therefore at a distance and that distance we are taking as y, which is given to us as a 5 centimeter, and that will be equal to 0.05 meters. And everything is same, so we can use that. We already know that whenever there is a point which is at the perpendicular bisector of the rod, and we have to find out here the electric field, then their horizontal component is going to cancel out from one this end, another this end. So electric field we can divide into two components, and this horizontal component will be balanced out, and that happens because of the symmetry. So you can say by symmetry we can say that our horizontal component of the field cancel, and only the vertical component survives. Vertical component survives. And once again, let us consider a small point that is our at a position x. So this was our rod, and we consider a small point that is at a distance of x, and this is our y. So it is having a charge dq, and length is our dx. Therefore we can write that for a small element dx at position x, we can write that our dq will be equal to lambda time dx, and this is our point B, and so this is our distance r. Therefore we can write that our r will be equal to x square plus y square and its square root. Therefore in general we know that the value of electric field is given as k dq, and this is r square. We substitute value of k, so this comes not k but r, so this comes as dq, and we have here x square plus y square. And like we said, only vertical component is going to survive, therefore you can say that its vertical component will be equal to dE sine of theta, if theta is the angle. So this is theta is the angle, and from the figure we can write that our sine of theta will be equal to, and this comes as our y upon r, and we substitute, so we get electric field in y direction, and this comes as k lambda dx x square plus y square, and this is our y upon x square plus y square and square root, and this can be written as k lambda, and we have this as y dx divided by x square plus y square and whole raised to power 3/2. So total electric field in y direction will be the integral of our this k lambda y, and integration goes from minus L/2 to plus L/2, and this is our dx x square plus y square and 3/2, and this integral, if we solve it, we are going to get this as e of y will be equal to k lambda y, and this comes as L, and we have y square square root of L/2 whole square plus y square. Okay, so this is the net electric field at B in y direction. And now we can easily substitute values. So k we already know is our 9 into 10 to the power 9, lambda is our 8 into 10 to the power minus 8, y is given to us as 0.05, length is 0.1 divided by, and this comes as our L/2, L/2 0.05 whole square and 0.05 whole square and its square root. So we get that electric field in y direction will be approximately 2.04 into 10 to the power 4 Newton per coulomb. Okay, and this is for point B. So this question was quite easy, and if you know the formula, you can just directly substitute the values and get the answer. And if you do not know the formula, you can just drive it, and then we can get the answer for that. Next question. And this question is quite easy. It has been, you can say, dealt many times, but here the statement is asked in a little bit different way. It states that a point charge q is located at the center of the cube of edge D. What is the value of the integral E dot dA over one face of the cube? And part B, the charge q is now moved to one corner of the cube. Now what is the value of the flux E through each of the faces of the cube? Okay, so it can take as time space, so this is the only condition. And in this case we are going to use Gauss law, or we can say in particular we can call this Gauss law as a Gauss law of symmetry. Gauss law of symmetry, particularly for these types of problem. And in part A, it is given that the charge is at the center of the cube. So let us draw a cube. So this is the cube, and charge is at the center of the cube, so it is somewhere here. And so this charge is given as our Q. Therefore, we can say by Gauss law, we can say that the closed interval of E dot dA will be equal to the charge enclosed divided by the epsilon naught. And based on this, we can easily write that flux through the entire cube, flux through the entire cube, let us call this as phi total, will be equal to charge upon epsilon naught. And we are going to use the symmetry, so we can say that by symmetry we are given charge is at the center, and therefore we can say that all 6 faces are equivalent. All 6 faces are equivalent. Or you can further write it that all flux is equally shared among the faces. You can say flux is equally shared among the faces. Therefore, there are total 6 faces and total flux is our phi t. Therefore, we can say the flux through one face let us call this as phi, then this phi will be equal to 1 upon 6 flux total, or we can say this will be equal to 1 upon 6 Q upon epsilon naught. And this was comparatively easy. And in part B, we are given the charge is at now at a, we can say, at one of the edge. So let us once again draw a cube. So this is the cube, and let us suppose charge is at this edge, and let us call this as A, B, C, D, and this is E, F, G, and H. So this is the cube, and charge is at our point C. And like we said, we are very much interested in Gauss law of symmetry. As in first case, the charge was at the center, so this was a symmetric position of the charge. Whereas in this particular case, the charge is at one of the corner. Here we have assumed at C, and it is nothing but asymmetric. So we have to make it a, or we can say we are going to construct a symmetric Gaussian surface. So we can say we are going to construct a symmetric Gaussian surface, and for that we are going to you can say imagine or draw 8 identical cubes together. So for this we are going to place, or we can say we are going to draw 8 identical cubes. So that the charge sits at the center of the larger cube. So we are going to draw 8 identical cubes so that the charge is placed at center of largest cube. So in this case, the question will be back to our first part. Okay, first part, the charge was at the center of the cube. So let us construct the cube, and so this is our cube, larger cube, and we are left with this portion now. And finally the last portion. So this is our larger cube, and our point of interest is this. This is our, we started with our A, B, C, D, E, F, G and H, and we are having this charge at point C. So we have made a symmetric bigger cube where the charge is at the center of the cube. So this is charge Q. This is our ultimate aim. And so it means that now let us discuss everything with respect to this larger cube, and then we come to our smaller cube. Therefore we can say that total flux of the large cube and let us call this as phi large will be equal to the charge enclosed and by epsilon naught. And this large cube we know is subdivided into 8 small cubes. You can say by symmetry the flux is shared by 8 small cubes. 8 small cubes. Therefore, you can say that a flux through a small cube will be equal to 1/8 of flux from the large cube. That comes as 1 by 8 and q upon epsilon naught. Okay, so we are able to find out the flux that will be associated with the one small cube. But we have to remember that for one small cube, the charge is at one of the edge, a corner, okay, vertex. So let's find out. There will be total 6 faces of the cube, and out of these 6 faces, how many will be able to get the flux. Therefore, let us identify which face get the flux. Identify which face gets the flux. Like I said, we have each small cube has 6 faces, and we are interested in finding out the points or face which are meeting the charge. So we are going to find out faces meeting the charge. And if you look closely, this point C, there will be total 3 faces which will be associated with this vertex C. Basically, C means our charge. The faces meeting the charge, and these are nothing but our 3 faces. And these 3 faces will be our ABCD, and that will be our backward is our CDEF, and the third one will be our BGFC. So these are the 3 faces, and which will be touching the corner C. We can say these are the 3 faces associated with charge Q. Okay, so these are the 3 faces, and therefore the electric field from the charge will not be able to cut through these 3 faces, and therefore we can say that our field will not cut through these faces, and therefore the flux associated with these 3 faces will be equal to 0. Or we can say that only because there are total 6 faces, so 3 faces will not be able to have association with the flux, so only 3 faces will be associated with the flux. So it means that only three faces must share the flux, and that flux is our phi of s, and that was our q upon 8 epsilon naught. Therefore, we can say that flux through each face and so we get this as our phi phase will be equal to 1 by 3 of our smaller flux. Therefore, we get that the flux through the face will be equal to, this comes as our q upon 24 times epsilon naught. So this was the flux associated with the charge which is placed at the corner of the cube. So the placement of the charge is very much important. Okay, and for this particular case, we can simply say that we have used the Gauss law, but specifically Gauss law for symmetry. Okay. Next question. So it states that charges plus 2q and minus q are located on x-axis at x equals 0 and x equal to a respectively. Find the point on x-axis where the electric field is 0 and makes a rough sketch of some of the field lines. So sketch is not required as such, and you should find that some of the field lines that start from 2q charges end up at minus q charge, while others head off to infinity. Consider the field lines that form the cutoff between these two cases. At what angle with respect to the x-axis do these lines leave the plus 2q charge? Okay. So let us discuss part A and then we come to part B. And in part A we are given that we have a x-axis. Suppose this is our x equals 0 and that other end is our x equal to a, and at x equals 0 we are having charge of plus 2q, and x equal to a we are having charge of minus q, and we have to find out where the electric field is equal to 0. So we can divide this entire into three regions. Let us call this as our region number 1, that is between x0 and xa, and on the left side let us call region number 2. So this is region number 2, region number 1, and this we call as region number 3. So we want that our electric field should be equal to 0, and so electric field can be only 0 when the two fields are in opposite direction. So you can say that only possible when two fields are in opposite direction. So out of these three regions we are going to first of all identify which of the region is going to have the fields that will be in opposite direction. So first of all let us discuss region 1. So region 1 is our x greater than 0 but less than a, and we have our plus 2q charge, and plus 2q charge is going to provide a field that is towards the right side, and then we have our minus q, and minus q will be also going to point toward the right side. One second. Okay. Then we come to our, therefore in this case you can say, because the direction of electric field is same, so cancel is not possible. So you can say cannot cancel. And then we come to our region 2, and region 2 is our where x is less than 0, and therefore we can say that the field due to our plus 2q is going to point toward our left side, whereas this minus q is going to point toward our right side. Therefore in this case we can say cancel is possible, is possible. And then we come to our region 3, and region 3 is for x greater than a. And once again we have our plus 2q, it points to the right, and from minus q it points towards left. So we can say the cancel is possible. So we have two regions. This, the electric field can cancel out each other, and that will be equal to 0. And let's discuss these regions one by one. So first is our region 2. In that case x was less than 0, and for that we have our, this is our x is equal to 0, x is equal to a, and let us consider a point at a distance d, and that is x is equal to minus d. And we are going to find out what will be the electric field at this particular point. Therefore first of all let's find out our distances. So distance from charge at 2q, that will be equal to d, and distance from charge q will be equal to, this distance is our a, so it will be a plus d. And now we can write the equation for the electric field. So electric field due to charge at 2q will be equal to 2kq, and this is our d square, and charge because of q we are going to get this as our kq a plus d whole square. And for cancellation we are going to simply equate them. So you can say for cancellation we can just equate them, and we get this as our 2 upon d square, because like terms are going to cancel out throughout, so this becomes 1 plus upon d square, and this will be giving us square root of 2 a plus d is equal to d, and this gives us that d is less than 0, and which is, or we can say no solution. Now we come to our region number 3. Region 3 for x is equal to greater than a. Same, we are going to just, so this is our x is equal to 0, x is equal to a, and we consider a point that is x is equal to d, and this is distance is our a, and this distance is our d. Same thing, but on the other side of our, on the right side basically. And once again we can say that the distances, that is our from charge 2q will be equal to a plus d, and from charge q, or not q but minus q, is our d. One second, this is minus q. And now we can write there directly, we can just equate them. So we can say this, can say that set magnitudes equal of the electric field. So E of 2q should be equal to E of minus q, and we get from here 2 upon a plus d whole square is equal to 1 upon d square, and this gives us square root of 2d is equal to a plus d, and giving us that our d will be equal to, this comes as a upon square root of 2 minus 1, or we can simply write this as a, we can rationalize it, and comes as 1. So this is our value of d, for which the electric field will be equal to 0. And this part B is actually quite interesting part. Okay, and we are going to find out that, okay, let me go through the part B. We have to find out the cutoff angle between the two cases. Okay, so basically it means that, so we come to part B. So we have our plus 2q charge, and this is our minus q charge, and the fields will be moving in this direction, and we know that after some of the fields will be also going towards infinity, something like this. Some of the fields will be going towards minus q, and some of the fields will be going to infinity. So we have to find out with respect to this 2q, or if this is our x-axis, then with respect to angle x-axis we have to find out what will be the angle at which these fields will be traveling to the infinity. This is the basic question. Or we can say, in the shorter version, we can say we are going to find out angle of separating field lines. This angle is sometimes also called as a critical angle of field lines. So we can say that angle of separating or we can also call this a critical field lines, or in more elaborate way we can find out that these are the field lines that just fail to end on minus q. These are the field lines that just fail to end on minus q. Okay, they start from plus 2q but fail to end on this minus q. And so we can use here let us start with a Gauss law argument. So you can say from Gauss law, we know that the flux that will be leaving our plus 2q will be equal to 2q upon epsilon naught, and flux that will be terminating at minus q will be equal to q upon epsilon naught. And we can easily find out what will be the amount of flux that will be going towards infinity, that will be not terminating at minus of q. And for that we can use the conservation of this flux. Therefore we can say that flux originating from plus 2q will be equal to flux terminating at minus q plus flux going to infinity. And we can write this as our 2q upon epsilon naught is equal to q upon epsilon naught plus flux terminating at infinity. Therefore we get that flux terminating at infinity is equal to our q upon epsilon naught, or we can write this will be equal to our half of flux starting from our 2q. So this we can use by the conservation law. So it means half of the flux will be going towards infinity, only half of the flux will be terminating at our minus q charge. And in order to find out the angle, okay, that is our critical angle, we have to assume a Gaussian surface. Okay, this is the key point, the assumption of the Gaussian surface. We can say let me write assumption of Gaussian surface. Assumption of Gaussian surface. Okay, so this is key here. Okay. And this Gaussian surface we are going to assume as a conical in shape. We are going to say take a cone with its vertex at plus 2q, whose plus 2q charge, whose surface follows the separating field lines. The separating field lines. So it means we are going to consider suppose this is a plus 2q, and we are going to consider a conical surface like this, and this is our axis, and let us suppose this angle is our theta. So we are interested in finding out this value of theta. So basically it means that the field lines which are lying within this angle of theta will be terminating at this minus 2q, and the field lines which are outside this conical surface, so this is our conical surface, and they are going to terminate at infinity, yes, approximately. So we are interested in finding out this value of theta, and for that we know that the flux that is going to infinity is our q by epsilon, which we have already calculated. So this is the flux that will be going towards infinity. So we have already our Gaussian surface, and we know that the flux to infinity which we have denoted as phi infinity is equal to q upon epsilon naught. And we can also find out the flux through the cone, and flux through the infinity is q upon epsilon naught, or we can also say that the flux through the cone is also our q upon epsilon naught. And we can find out by the solid angle. You can say that the flux through the cone from a point charge, flux through the cone from a point charge, and let us suppose this is your phi, and that phi will be equal to over q upon epsilon naught solid angle divided by 4 pi. And so these two is same, so we can just equate them. Let us call this equation number 1, and this is equation number 2. You can say from equation 1 and 2, from equation 1 and 2, we can write this as q upon epsilon naught solid angle 4 pi will be equal to q upon epsilon naught. And one second, there is 2q, and this cancel by epsilon goes out, charge and charge goes away. So from here we get that our this solid angle is equal to 2 pi. But we also know that the half angle of this cone is our theta, so we can write that solid angle of a cone for half angle theta, we can write that solid angle is equal to 2 pi 1 minus cos of theta, and this is equal to over 2 pi because we already found out solid angle is 2 pi. So this 2 pi and 2 pi cancel out, so we get this as 1 minus cos of theta is equal to 1, and this gives us that our value of theta is equal to 90 degree. So for this value of theta, we are going to get that the flux will be at infinity. Okay. So we can just, because initially we have taken that our cone is something like this, and this angle was of theta, but now we found out this theta is equal to 90 degree, so approximately, okay. So you can say this will be something like this. So value of the electric field will be going like this from our plus 2q, and these two will be going to infinity. And so here we come to the next question. So this, in this case, we have to, the only important part is the choice of the this Gaussian surface. So this particular case, we choose the Gaussian surface to be conical in shape, because the boundary line is the surface of the cone, which can easily segregate or divide the field line that will be ending at the charge minus q and the field line that will be going towards infinity. So this was important in this case. Next question. And so here it states that a ring with radius r has a total charge q uniformly distributed around it. To leading order, find the electric field at a point along the axis of the ring, a very small distance z from the center. This is only, the question is little bit tricky, otherwise the solution we have done this many times. And part B is consider a small cylinder centered at the center of the ring with a small radius r0, small height 2z0, with z0 lying at either side of the plane of the ring. There is no charge in the cylinder, so the net flux through it must be 0. And this part B is basically true and false question. Okay. So first of all, we are interested in the ring, and for our this a point on the ring, and that is a small distance z from the center. Let us go, this is point P, and this is center, and it is at a distance z, and we have a radius is our r. Okay. And this we can use the direct formula. We can say that the electric field on the axis of the charged ring, the field on the axis of charged ring, and let us call this as our z direction and at point z. Therefore we can say that our E of z in z direction will be equal to 1 upon 4 pi epsilon naught, and this comes as q times z, and we have this as r square plus z square and 3 by 2, and direction will be along the axis by symmetry. Okay. And we are going to find out that for z, which is very much less than r, we are interested in that, meaning our denominator we can say by r square plus z square and 3 by 2. So we are going to take r square as common, so this will be coming as r cube 1 plus z square r square, and we have this as 3 by 2. And from binomial expansion we can say this is approximately equal to our r cube. Therefore the leading order is going to give us that electric field at point z in z direction will be approximately equal to 1 upon 4 pi epsilon naught, and this is our q and our r cube and our z. And okay, so this was our part first, and then we come to a part B, And part B, it is given that there is a small cylinder and that is symmetric about the center. Okay, so we can just draw a small cylinder. So this is a small cylinder, and suppose this is the plane of the ring, and this is the axis of the cylinder. So center is somewhere here, and this cylinder is symmetric about this axis. So we have z naught on the positive side as well as z naught on the negative side. So total length of this is given as twice z naught, and radius is given as r naught. So in this case we are having the flux contribution will be because of three surfaces: top surface, bottom surface, and the curved side. So you can say that the flux contribution will be because of top face, and top face is our z is equal to plus z positive, and then we are having bottom face, and bottom face is our z is equal to minus of z naught, and finally we are having the curved side. So let's find out what will be the flux because of the flat surfaces, and we are going to use our part A in this case. So you can see that our flux through the flat face, and we already derived that the E of z in z direction is our q upon 4 pi epsilon naught r cube and z. So we come to our top face. Top face is giving us z is equal to plus of z naught. Therefore we can say that the flux because of the top face will be equal to, by Gauss law, is our electric field at the top surface, which is z naught, and its area pi r naught square, and we substitute it. So we get the flux because of the top surface will be equal to q upon 4 pi epsilon naught r cube, and this is z naught and pi r naught square. Now we come to our bottom face. Bottom face is our z is equal to minus of z naught. Okay, and in this case we can write that the flux because of the bottom will be equal to same q upon 4 pi epsilon naught r cube, and this is z pi r naught square. Okay, in this case we have to remember that no doubt the direction of field is opposite, but the normal direction is also in the same sign. It is always outward, especially in the case of bottom face. So both are in same, so sign is going to remain same. Therefore we can write that the total flux through the flat faces total flux through flat faces let us call this as phi flat, and we get this as phi flat will be equal to addition of these two, and this is same, and it will be coming as 2 epsilon naught r cube and z r naught square. Now we come to our flux through the curved side. Flux through curved side, and which we count as a radial, and for that we have standard formula that is -1/2, and this is our q upon 4 pi epsilon naught r cube, and this is our r naught, and the side area element for a small element dA, that will be equal to over 2 pi r naught multiplied by dz, that is a small element. Therefore we can write the flux through the side, let us call this as phi side, will be equal to, and it will be our limit from minus z naught to plus z naught, radial electric field at r naught, and this is about 2 pi r naught times dz, and so we get this as phi side, flux through the side will be equal to -1/2 and q upon 4 pi epsilon naught r cube r naught 2 pi r naught, and this comes at 2 z naught, because the rest all the things will be constant, only z is our, so this comes at 2z, and we can easily solve this. So this goes by 2, pi goes by pi, and this goes by 2, and rest we are same. So we get the flux through the side will be equal to minus q upon 2 epsilon naught r cube z naught and r naught square. And now we come to our total flux through the cylinder. Total flux through the cylinder, and let us call this as phi t, will be equal to flux because of the flat surface plus flux because of the side, and so this will be giving us flat was over q 2 epsilon naught r cube z naught r naught square minus side was 2 epsilon naught r cube z naught r square, and these two terms cancel out, therefore we get the total flux through the cylinder is equal to 0. And this was true based on our Gauss law also. If you look closely, the question it mentioned that there is no charge inside the cylinder. Okay. If there is no charge inside the cylinder, obviously according to the Gauss law, the flux associated with the cylinder has to be equal to 0. This statement is our true. So we can also deal it directly, okay, but if we want to do it analytically, so we can find out the flux through the flat surfaces, flux through the side of the curved surface rather, and that gives us their summation will be equal to 0. Okay. So this completes all the questions for today. Thank you.